Thank you so much. That was a wonderful introduction. So let's see, a bit about myself. I'm an engineer, spent most of my career at Qualcomm. And there I worked on operating systems. If you guys are old enough to have ever held a flip phone, those, like a CDMA flip phone or like a Motorola Razr, they ran a software called Brew. So I was a core kernel developer. By object size, I wrote more than half of the kernel because I wrote the compiler that generated a bunch of the code. So after that project, I ended up working on these DSPs that are on our processor. And these things have a modern mobile chip has a bunch of different components all shrunk to the same die. And if you think of it as a distributed system, how we solve our problems there is by timestamping everything. So you have a bunch of messages coming in from like accelerometers and cameras and like everything else. And your power management system starts kicking things on and off. And your operating systems, some are real time, some are not. And things get completely out of order. So when you try to actually make sense of the data and produce like a 3D image or something like that, you don't know when events actually happened based on when they arrived into the renderer. So if we timestamp everything, because we have a single clock and we can trust this clock everywhere in the system, we can then order all the messages before we actually process them and like create this scene. And then things actually look more like real life. So this optimization, it's kind of commonly known as like read consistency. So Google also uses this in their global databases. They call something true time, which are these like atomic clocks that they've synchronized with precision. And because it's their own databases and their own clocks, they can trust the timestamps from all these clocks. And when messages arrive, they can order them exactly the same way everywhere in each database without talking to each other. So the inspiration for Loom kind of came from my experience as an embedded systems engineer. And Intel actually released a platform called SGX, which is a trusted core, which you can also use for verifiable timestamps. Our approach is all in software, so you don't have to trust us because it's based on a cryptographic process. So let's see. So what's Loom? Loom is a high-performance, fault-tolerant operating system, or blockchain. And it's based on kind of the core component is called proof of history. And that is our way of encoding time as data, and actually like passage of time as data. And how it works is actually fairly simple. So if you guys are familiar with what a hash function is, it takes a bunch of data and then generates a piece of data that's the same size. So it can be 256 bits, could be 512 bits. But the property of a cryptographic, or more specifically a pre-image resistant hash function, is that you can't predict what the output is going to be when you run it. So if we take this function and we loop it over itself, so its next input is the previous output. You can kind of run it over and over. It's a process that you can't parallelize because you don't know what the value is going to be a million iterations from now. You actually have to spend some actual time running this thing a million times. So if we sample this process as it's running and we record the counter in the current state, we get these ticks. So if you look at this data structure, you can actually infer that time passed somewhere for somebody to generate it. And that's kind of like the crux of this proof. So we can use this data structure also to kind of give ourselves this read consistency of events that are happening outside. By that I mean is that like when I examine the data structure, I can look at it and I know that these two events happen like within half a second from each other without me actually having to observe them. And the way we do this is we take some blob of data and we append it to this hash function as it's running to its state, and then record the counter and what we appended. So that could be in itself a hash of the data that you're actually recording. But now our data structure contains these ticks and some data that represents an event that occurred sometime. And we know that the hash that's generated right after that occurred after this event that was created. You guys are following me? Do you want me to go like upper or deeper?
Deeper.
Deeper. Yeah. So what's cool about all this is that while it takes real time to generate, if we take each one of these ticks from start to the end, we can verify each one in parallel on a separate core. So a modern GPU card has about 4,000 cores. So if you have a second and 4,000 ticks, you can verify those 4,000 slices in parallel, and it should take about a quarter millisecond, plus or minus the difference of the CPU running times on the GPU and the CPU. So that means we have this like nice asymmetry between generation, which is real time, and verification, which is parallelizable. So, and GPUs are fairly cheap these days, and Moore's law is working in our favor because you can add more cores, but it's very hard to get a core that's faster. So we can also make this data structure self-consistent from an external user's point of view. And how we do that is, me as a user that's using this service, I can take a hash that's part of this historical record, record it in my data set that I'm signing, sign it, and then take that signed blob and insert it into the next set, into the next hash as it's being generated. So now we have this like stream of data that has signed blobs which point back in time to a hash that was generated before. So now like an untrusted generator can't reverse the order of any of these events because that would change all the hashes and then they won't appear in the previous record. So now these events have an upper bound and a lower bound of when they occurred. So we only need one core in the world to run this, and we can potentially record every event that's happening in the world with cryptographic certainty. So like 100 years from now, you can look back in history and know that like this event happened now and this event happened like 2 seconds from now. There's something really cool about that, and this is why like what's driving me to build this. Because we can now have history that is more certain than we had history before. So some nice properties of this is we can take multiple clocks or looms, and we can start sending hashes between themselves. So now in our record, if you have two of these generators, there's a synchronization point between them. Again, if you imagine this is like a science fiction project, you can have one on Mars and one on Earth, and if they start synchronizing, now when you merge those two records, you kind of have some cryptographic certainty of when the relative order of events occurred between stuff that's happening 24 minutes away from now, right, on Mars. So this record, it doesn't do anything with consensus. And consensus is kind of like the problem that most people talk about in blockchain. This is simply just read consistency. So it's a self-consistent order of events. So anyone can potentially generate a separate order and a separate history that's going to be completely different. So consensus comes in selecting a unique history that everyone in the network agrees that that's the one we're actually using. So when you combine this with like proof of stake, you can actually get a blockchain where consensus occurs over a historical record, which can encode as many transactions or changes as like network bandwidth allows. So now we've separated the transactional throughput from consensus, and that's kind of like the key part of how we can scale to as many transactions per second as possible in the network. So what's cool about this is we can actually build a proof of stake system with high availability. If you guys know what cap theorem is, you have to pick either consistency or availability. We can actually pick availability with some human bounds. And that means that when there's a network partition, that we have enough human time to figure out which one we're actually going to pick with. So imagine this is kind of like what our network looks like. There's a single generator and a bunch of replicator nodes that are replicating the state. And Yellowstone blows up. And now we have two networks that are separated. So the smaller network and a larger network all start forking on a different set of histories, right? But because the smaller network has fewer verifiers that are verifying with their like consensus, their proof of stake based verifications, it recovers much slower. And this one can recover much faster. So now those differences in time is what gives us humans like time to figure out, okay, the smaller one is just like a faulty internet cable, and we're not going to actually commit to using it because we know that this larger one is still there and it's going to recover much faster. So I'm not going to trust the smaller one for my transactions. So if you want to visualize that, it kind of looks like that. You have a bunch of transactions that are happening, and there's a partition, and one of the partitions has 1% of the verifiers left, and the other one is 99% of the verifiers left. Because those 99% are present, the state machine can then infer that 1% can be unstaked very quickly. And in the other partition, because the 99% are absent, it's going to take a very long time, non-linear, right? Like human time frames, like months potentially to unstake the full 99. So we can actually take this data structure and recover it from every point, and that's something that I think might be unique to this particular proof of stake implementation. Like Bitcoin, if you think of this ledger, all the computers in the world can blow up, and we can start doing the ledger by hand and solving the hashing problem by hand, and that's still a valid blockchain because we are continuing the protocol, right? If you had a simple proof of stake system like Tendermint and half of the network died, you would have to effectively hard fork and figure out which side of the network is actually valid. So with us, instead of doing a hard fork, the generator actually has to prove that months of time passed and that there was really an absence. And then when you look at this ledger and you compare them, you actually have availability encoded into the ledger. So when you have to figure out which fork is the right one, the one with over 50% verifiers is the right one. So we kind of have this like true height of the blockchain encoded into it. So if this is kind of like how the message flow from the verifiers and the generator. So one of the problems with doing like scaling this thing is that the amount of network bandwidth we have in any single point of the network is, so the total network bandwidth of how many transactions we can do is going to be limited by the smallest link in that network. So if you have 1 gigabit connection, every node in that graph can only process 1 gigabit. So you can only do 1 gigabit total for the entire network, even if you have like 10,000 computers. How we can kind of mitigate some of the effects of this is by forcing the verifiers. So in the initial round, if you guys look at this, some of the messages flow to the first set. And then we can do something what BitTorrent does, which is start fanning out the bandwidth. So how that works is we split this bandwidth by 1 over n, right? And then this first layer nodes, we put all the data together, and now we have 3 times as much bandwidth. So now, like, to serve like a global network for payments, we can actually quickly fan out and multiply the amount of bandwidth available for the entire ledger for everyone to observe. Using very similar methods to Brian Cohen's BitTorrent. So how we're using this proof of history thing, so we can force very quick finality, and we can force the verifiers to actually do their work within a certain amount of time. And if they don't, they simply don't get credit. Because every node in the network can trust this like historical record of events without actually observing it. After a bunch of transactions, there's some still proof of history stream that's being generated. We start seeing verification events. And if they all arrive within half a second or 500 milliseconds, then they get a reward. If they don't, then they don't get a reward. So everyone that is in the network that sees this data structure, they can trust this order of events without actually having to be in the loop of observing these messages. You guys following me? Cool. So one of the problems with having a centralized, kind of a central generator is censorship, because this thing is our ingress point, or the point where all the messages in the world have to be encoded into the stream. So how do we know that it's not like censoring users? Well, how do you prove censorship? You can't. You can actually only show that there's some packets being dropped. So, because like, I don't know if I sent this packet and it actually died on the network, or this verifier actually decided that they don't like me and they dropped it. So what we can do is the users can actually forward their messages to the verification nodes randomly. And those verification nodes can forward it to the generator and then observe if this packet is actually encoded into the stream or not. And between all the verifiers, they can maintain a median error rate. And if that error rate gets too high, they can simply kick that generator off and go to the next one. And it doesn't really matter who is continually creating this data structure, because the data structure itself is our social truth. It's not tied to any particular identity. We only really trust the ledger and the data as it's encoded. So again, this solves some of the censorship problems. The other problems, I think you would have to solve in like higher levels, which are more like using ZK snarks and more privacy-related cryptographic applications, as well as changing the behaviors of the users. So, because users can create 1 million wallets with 1 million private, 1 million identities, and they can randomly, like when I have to pay somebody $1 million, I don't have to pay a single transaction of $1 million. I can pay 1,000 transactions of random amounts from random wallets. And because we're like running at the throughput of just network speed, our transaction costs are ridiculously cheap. It's literally the cost of updating memory, right? And that should be like 10 to the, according to my calculations using AWS, it's about 10 to the minus $6 per transaction, right? So like, if you look at like McKinsey reports about payments, there's what, $40 trillion worth of volume, and $2 trillion is how much we pay in payments. So it's 5% tax in the world economy, and it's absurd that we have to spend that much to like transfer money, like transfer numbers around in a computer system, right? Like it should be really the cost of updating memory. In my view, that's just a huge regressive tax on like the world economy. So let's see. So interesting thing about this is that often comes up as a question. What if somebody had like a really fast computer and they could like outrun the system? So let's go back to the slide. So what would happen is the generator could potentially take this 500 milliseconds and actually wait 250 milliseconds and then generate 500 milliseconds worth of proof of history proofs and reorder messages. So if they had like a verifier that was in cahoots with them, they could encode their message earlier and they would get credit. That basically devolves in a system called delegated proof of stake. So there isn't an opportunity to create a double spend, but it's an opportunity for somebody with crappier network to kind of get credit when they shouldn't. And how we solve that is by effectively having the fastest ASIC. So a modern day AMD Ryzen core can do SHA-256 round and 1.75 cycles. It's actually, I think, very hard to get much faster than that, because if you guys look at this green path, it's pretty long. So typically, like a modern CPU will have all of these stages pipelined, so every adder is in a separate clock. And if you do some special instructions, you can kind of combine things. But if you try to do this whole thing in a single clock, your clock is going to get very slow. Like it's going to be much longer clock speed. So unrolling this and kind of stringing it together will quickly get diminishing returns. So the first person to roll this ASIC will probably get 99% of the way to all the optimizations you can do. And we're probably going to do that because I spent 12 years at Qualcomm, and I think hardware is fun. The cooler thing about like rolling our own ASIC is we can build a board that can handle like a 24/7 liquid nitrogen cooling, which should give you about 30% boost, and that would be awesome. And that's cheap enough to run like actually in a real network. So that's basically it. You guys have questions? So was Brian Cohen more technical? Was the Chia Network guys more technical? Or?
I think he wasn't able to present that day. It was somebody else presenting that day because
cool.
he had some conflict. Correct me if I'm wrong, but you're saying you'll build this not for a mining reward, but just for the overall health of this network.
Yeah,
There's no mining reward.
If the question was, is there a mining reward based on the speed of the clock? There's not, but the network would set a minimum clock speed, so if you can't keep up, you would get kicked out effectively. You wouldn't be able to keep up with you wouldn't be able to be selected as a generator.
So can you talk a little bit about distribution of
tokens?
Yeah.
There's no tokens, there's no security, this is just software and an operating system. But some economics play in part with the proof of stake system. We can actually use proof of work. It doesn't really matter what these verifications are, as long as there's some Sybil resistant way to measure votes. And if you guys don't know what Sybil, the Sybil attack is spoofing identities, like, internet voting. I got like 1 million likes, was that really 1 million people or just 2 people with a bunch of bots? So how like Bitcoin does it is you buy a bunch of ASICs with separate cores and they spend all this time and electricity generating random numbers to figure out a puzzle. So the person that solves that puzzle first gets some credit. But because of the hardness of the puzzle, we can kind of infer how much electricity went into it, and that's your way of proving identity. So you're basically voting with electricity. With a proof of stake system, you're taking some of the tokens in the network and you're saying you're not going to spend them and they're going to keep them in a separate account and you're going to vote with those. So it's based on like kind of cryptographically proven identities secured by your private keys. It's in a way weirdly recursive because you're using the network's accounting system to vote for its own accounting system. But so in our proof of stake system, the verifiers would get the fees, right, and part of the mining return, and there would be some way to distribute that. Those kind of token problems we haven't simulated yet. That's like that's more of the step 2 part.
Thanks.
And there's a lot of ways that could go wrong.
So you mentioned that you have or you can construct this mechanism for verifiers with a consensus that a generator is censoring information. Is there a way to detect cases where the generator is reordering events relative to what event creator is generating?
Sure. So the generator will have some opportunity to reorder events, which is the gap between this observed, the last thing that the user signed, and when they're entered. There's no way to really detect that. So effectively, those packets are in flight. So for most transactions, like paying for coffee, it doesn't really matter. But for things like maybe order book settlement on an exchange, that might matter. So those could be solved with use case specific solutions. For example, for an exchange, when you have a bunch of orders, you can actually decide the final order based on a random number generated in the future.
Oh.
So there's interesting approaches to all problems. Or like users could actually change their behavior and generate many different small orders because it's so cheap to insert them. So then this thing has really kind of no way to figure out what the market action is happening,
Thanks.
Please, go ahead.
Can you explain again how conflicts are resolved, or you think there are no conflicts?
So conflicts in the sense if there's a partition.
Right.
So let's go back to this one. So let's say, right, there's a partition occurs here, and maybe somebody in the network is still connected. They would see two different historical records, and their Sybil-resistant identity has to vote for one or the other. So the conflict resolution occurs by means of voting in the consensus scheme, right? So you have two different historical records. You, as the verifier, have to pick one, and you can't vote on both. And if you vote on both, then you can use that proof. That you can, if somebody sees you voting on both, they can submit your double vote on the other ledger and slash your bond. If that makes sense. It's this process called slashing, which was introduced by Ethereum, probably before Ethereum, but they kind of maybe made it famous in their Casper proposal. Does that make sense? So if there's no like two valid, you can have as many valid. Oh, sure. So for example, we had where's our partition? We have two historical records, right? The verifiers have to pick one or the other, and when they pick, they take the last observed hash that they've seen, they sign that transaction, and they sign it with their identity, which represents some of their voting power, and they submit it into the historical record. So now they have to pick one or the other, because if they try to pick both, then anyone that presents their signed message of picking two different historical records can then present it to a historical record and cause their bonds to be slashed, which means that their voting power gets removed from the system, and that's a loss of capital. So it's as if you're hashing on both Bitcoin Cash and Bitcoin at the same time, but then because you're doing that, your ASICs burn up, because you can't do both, right? You have to pick one or the other. So this is like a softer way of emulating that. So we don't, effectively, if there's a partition, the one that gets to 2/3 of verifiers is the true one. The other one gets dropped. And you as a client, you can observe these verification messages and effectively see how much consensus has been achieved. Go ahead.
Right. So to follow up with that, how do you define which partition is going to be the dominant one? What if you're having partition, right in the middle?
A random process.
Like flip a coin?
Yeah. So the verifier sees both of these are near even. I'll just pick one. I'll pick one.
And it doesn't matter which one.
It doesn't matter which one, because ultimately,
What happens to the capacity of the one that's abandoned?
So those transactions effectively get dropped. And you as a seller, you wouldn't ship the product until you see 2/3 consensus, right? So you effectively, you submit something as Yellowstone blows up and you don't see 2/3 consensus, you're kind of stuck waiting for that to occur. So in this particular case, let's say 30% of the network dropped, or 34% of the network dropped. But that's an event that could occur, because AWS could go down. So that would cause the network to be in the state where we can still accept transactions, and you would only see less than 2/3 consensus appear. It's up to you to decide whether you want to give this person an item or not, but you can then go and look what actually happened. Is this an actual event that matters, or is this a non-event? And if this is an event where those computers are actually gone, over time as these proofs are generated, those missing bonds would get unstaked and the network would gain over 2/3 percentage. So if it's 1%, it happens quickly. If it's near 1/3, it'll happen in hours, right? If it's more than a half, it'll take days. If it's near zero, it'll take months. So we can kind of encode this into the protocol after doing a bunch of simulations and figure out, okay, in human time frames, if 1% goes away, it doesn't matter. If it's 20%, that's actually an event we should care about. And we should maybe spend an hour waiting for consensus again.
So if you have two networks, they're split, eventually they're going to merge back together again?
No,
the
the smaller one gets dropped. Forever.
So East Coast, West Coast, East Coast is trash.
If there's a war, yep.
And you said earlier Mars versus versus Earth. That would be separated networks, I assume.
Yes, those would be separate
How are they
networks.
going to sync up?
So they can
Or is
sync.
Mars just gone?
You wouldn't sync up. So those would effectively be separate networks with separate accounting systems. But they could still sync up and see relative order of events for things like maybe an exchange where you're trading things.
So they're not going to be one combined chain.
I don't know how to do that well. If you do, you should publish a white paper.
Would it be more,
I thought that's what you were suggesting.
those things, would they be more frequent here?
Sorry, which things?
Those splits?
20% dropped in availability would be, I think, very infrequent. Because that means that, like, if we have 1,000 computers, 200 of them randomly in the world disappeared. I would say that's a fairly low probability event. Like, given our internet infrastructure now, and as it's improving, like availability is something we count on, like, constantly, right? Like, my watch never gets disconnected.
So they still need to like sync up later on, otherwise they're gonna like eventually like 200 go away, another 20 go away, and it's just slowly gonna diminish down to zero.
Well, typically it's random, right? For the most part. For like unrelated events, right? There's some random number of computers are going to be down. And when it's a small percentage, then we can remove them from the voting pool quickly. But if it's a large percentage, unless there's a war, internet cables are getting cut, we can actually like start to think about how to repair those faults and like bring those networks back together. But clients that are participating in the network can ignore the smaller one because they know that the bigger one's alive. But if Yellowstone actually did blow up and we were only left with 20% of the verifiers, we can still continue processing. And us as humans that are like deciding to use the system can pick the 20% one and actually stick to it, and eventually it'll recover, and all those transactions will become truly finalized.
So the smaller one is like 20%. If they want to sync up their own, they would reset their whole state and then start over.
All those clients would have to resubmit their transactions because of this property here, where any of the last caches have to be present in the historical record, right? So if there's a partition, any new transactions added there will be invalid on the other one. And that's also a defense against a falsified ledger, because when I'm presented with a ledger as a client, I can look in its historical record and see if the 100 or whatever transactions I've done over the past 6 months are there. Go ahead.
So you mentioned that you want to design your own ASIC, as a means of getting to the absolute limit of time and utility. I'm sure that that hardware is going to cost money.
It's about $1 million.
How much?
At $1 million.
Up to $1 million.
Up to roll your own ASIC, it's about $1 million.
For the first one.
So,
For the first one.
so do you think there's going to be a centralization of the mining power, and do you see this as an issue?
No, because like that's just for like version 1. Once the pipeline is established, it's fairly cheap to version them and to go to the next fabrication level. So once you kind of design the ASIC and you roll it, improvements in the fabrication process are like not free, but they're much cheaper for you to leverage. You still have to do some tweaks in the routing and stuff depending on what changes they make. So it wouldn't cost us $1 million, and it's not $1 million that everyone in the network has to pay. It's just some group of people can collectively decide, here's an open source project, let's go fund it, ship this ASIC, build a board that can do 24/7 liquid nitrogen cooling, and we have the fastest possible way of measuring cryptographic time.
Well, just the point that you mentioned about Chia. Chia's whole point of that is to create the consensus as distributed as possible.
Yeah. So here in a proof of stake system, it's as distributed as people have, as they want it to be, right? It's just keys. There's no storage or anything required. Go ahead.
So So you have to store every single hash, as you mentioned,
Yeah.
and potentially you generate hashes on top of hashes. So isn't it prohibitive in terms of storage, and doesn't it get worse
So-
as hardware improves?
So no, because we're sampling the stream, so we don't have to store every hash. We can just sample it every quarter millisecond, or something like that. So we can sample like every 300,000 hashes, and when things get faster, every 3 million hashes. But storage is a problem in any blockchain that claims scale. So 25,000 transactions per second is about a petabyte of data a year. So any blockchain that claims scale has to solve storage. I don't know if you guys are familiar with Filecoin's proof of storage. So I wish I should have added slides on that. But that's an interesting problem, because how you verify that a particular chunk of memory is stored is a user encrypts it, and that encrypted data can then be used as your proof. So every unique key that's used for encryption can then be verified by me as the verifier. Can take the data set, encrypt it, and then compare the proof that the so-called replicator generated. The problem with kind of doing that is that the replicator can start encrypting the data and with many identities and deleting the stuff behind them as they're encrypting it. So every proof can be streamed. So Filecoin's proposal is to reorder the blocks every time you're generating the proof. That means that me as a verifier, I have to have the entire data set available to me. For every replicator identity, I have to encrypt it, right? The entire block. And so for every replicator identity, I have to have the exact same amount of space as the actual thing I'm trying to store. Does that make any sense to anyone? Okay.
Temporary space.
Yeah, temporary space. But if I'm verifying like 1 million identities that are all stored a terabyte, I need, over some amount of time, access to that much storage, right? So for us, we can actually leverage our proof of time thing, because while you can stream, you can still encode the data in a single order. We can force you to sample every block, let's say 1 byte out of every megabyte block. And you do this faster than it takes to encrypt, and you submit these proofs to this proof of history stream. We then know that you have had all the blocks available to you. And after about 6 samples, the probability of you deleting a single byte in every block drops to like 10 to the minus 6, 10 to the minus 4, something like that. So we can actually do very cheap to verify proofs of replication. So our solution to the storage problem of 25,000 transactions per second is a petabyte of data a year is using this to build a storage network that stores the ledger itself. So all of your kind of historical record can now be in this distributed storage network that's using these cheap to verify proofs of replication to guarantee availability of that. You can't use those proofs for consensus, because I could dump like a bunch of storage in the network, even if it's valid. The verifiers would run out of CUDA cores to verify all of them. So effectively, our network can give an economic incentive for you to provide storage and kind of earn credits for it. But it's not used for a consensus mechanism. Make sense?
Can you go back to the Yellowstone slide?
The what?
The explosion?
Oh yeah, it's my favorite slide.
Yeah, I love this. And I know one forwards. So the generators and the verifiers have vastly different hardware requirements. Because the generator needs to be like super fast to the core, and the verifiers need to be like a bunch of parallel cores. So how does one get spontaneously promoted to being a generator? Is it like an election process? And isn't that Loom B generator going to be like totally incompetent at being a generator? It's not a 2D ASIC.
So those, if we roll our own ASIC, those ASICs would be like cheaply available, because the cost is just upfront cost to do the fabrication, but then the cost per chip is like negligible, so we can give them out for free. And I don't even know if it'll be faster than AMD's and Intel's like specialized chapter 56 instructions. Because anything we unroll, we have to lower the clock speed. So the only real benefit is maybe making it easier to cool. So like there's Again, it's not even an attack that would allow you to double spend. It's simply a way for us, if we have the fastest clock, then synchronization, things, we can, I think, build more interesting applications on top of this.
But it seems like there's no incentive for a random person to run a generator.
Well, the network can select a minimum rate.
Okay.
So the verifiers have an economic incentive to have the highest quality network. So they would select a rate that's available to 2/3 of the network. So if you can't keep up, you wouldn't be a generator. And the generators could be selected randomly or election or some other process. It doesn't really matter because the source of truth is the data structure. So it doesn't matter who's appending to it.
So if the generator keeps changing?
Yeah, one of the interesting problems is called tragedy of commons. It's how do you actually know that these verifiers are doing their work? Like how do you know they're verifying these proof of history hashes? So the generator in our protocol will randomly insert an error as if its hardware failed, so with a small probability. And if any verifier approves that data structure, then they can get slashed. So that error should occur with like probably roughly every 10 minutes. And if it doesn't occur, they still get moved to the next available generator. And we can actually do the move without any gaps by doing this between the current generator and the next to be selected one. If it's a process that's known ahead of time, which it probably will be, because to do high transaction throughput, you need a high availability system, so kind of have to pre-select everything up front. Go ahead.
So there are presumably rewards for both generating and replicating, correct?
Yes. The economics, there's no tokens, it's just an operating system. We haven't worked out the economics of this, but there will be some economic incentives set up for that to work. Go ahead.
Is it going to be public which IP you send your transactions
So you can send them to any verifier and they'll forward them to the actual acting one. So you can, like as a client, you do discovery through like probably through Tor, DNS, and IPFS, you know, however you discover Bitcoin now.
Question.
Yes.
So who wants Loom today?
Who wants it? We think the most useful use case is a decentralized exchange that's running directly on chain. If you guys look at EtherDelta or 0x, and this is not to say anything negative about those teams, they're awesome. The settlement and everything occurs off chain. So that means that there's opportunities for the relayers or the makers to insert their own orders, and you would never know. Because we can enable this like high transaction rate, we can actually do all the exchange messages on chain themselves. That means the order book is part of the replicated state, so the opportunities for front running or queue jumping are like almost fully eliminated. And we can do the trick of deciding the final order with a random number later to really kind of eliminate them completely. So what's cool about that is the data then that's being replicated is then like tier 0 exchange data that's very expensive from NASDAQ, but now it's democratized and anyone can look at it and build their own bots and their own kind of trading algorithms and use them openly without like any friction. And I think that's awesome.
Why aren't you doing a token set? Why are you not doing a token set?
I can't even talk about that. Talk to lawyers. Don't talk to me. I don't know. I don't know anything about tokens. Apparently, like keeping track of numbers in a spreadsheet is a criminal offense these days.
What's your plan for the next 3 months? We're now ending Q1. What does Q2 look for you guys in Q2?
So we have like, if you go to our site, there's a GitHub, there's a bunch of code. We have like a V0 reference design of the proofs, and we're working towards making that like actually a real implementation. So by June, I think we'll have a testnet that we can actually call a testnet. Go ahead.
When you guys launch the testnet, say, how are you going to, or are you going to invite people to be generators, or are you guys going to just try to?
I don't know. I would look for like people that want to participate in the network. I think one of the hardest problems about building a public decentralized blockchain is that you're not only building an operating system, you're building a social network. So I'm hoping that because we can do this distributed mining, that non-sophisticated users can provide storage that'll enable some of the diffusion of getting this technology to a wide group of people. Because in my view, I think the mining is what makes both Bitcoin and Ethereum successful, because people can throw together really crappy hardware in their basement and like add value to the network.
Last question?
Yes.
Are you hiring?
I don't know. Are we hiring? Yeah, we're hiring. Yeah, we're hiring.
Is that a criminal offense?
No, I don't think that's a criminal offense. Yeah, we're hiring.
All right, thank you very much.